numerical aperture of given optical fiber. So firstly, I would like to tell you what is the optical fiber. Optical fiber is a kind of waveguide. It is a waveguide which is guiding the light wave, as the name suggests, optical fiber. Okay, so it will be guiding the light wave through it and make it be transmitted to the receiver end. Okay, so it's a waveguide which guides light particles or photons by the phenomena of total internal reflection. So TIR is the basic principle of working of optical fiber. Now our aim of experiment is to find its numerical aperture. Now what is the numerical aperture? It tells you about the how well the optical fiber is working, and it tells you about the light gathering ability of the fiber. How much light can be gathered by the optical fiber? This is given by the constant, that is the numerical aperture. So it is actually depicting the efficiency, or you can say the quality of optical fiber which we are using in our application. And then we have to find its acceptance angle also. Now I will be showing you in the coming slides that there is a direct relation between numerical aperture and acceptance angle. Once we find the numerical aperture value, simply by taking a sine inverse, we can get the acceptance angle also. Okay. This is the link where we'll be doing our virtual experiment again. Okay. Once I explain you the theory part and how to perform it about the experiment, and then we will move on to this particular site to see how it actually working. Okay. So as one of the students mentioned that it is a glass cable. Yes, it can be made up of glass also, it can be made up of plastic also. Okay. So here you can see these are fine transparent glass or plastic fibers which propagate light waves. It is working under the principle of TIR, total internal reflection. What is total internal reflection, class?
मैम जिसका क्रिटिकल एंगल से जब एंगल बड़ा हो जाता है टोटली
Yes.
रिफ्लेक्ट हो जाती है.
So what happens when incident angle is greater than critical angle? The light gets reflected back in the denser medium, right? That is the phenomena of total internal reflection. So obviously we have to create a refractive index, like we have to create a difference in refractive indices of two mediums, then only TIR phenomena can be observed in the optical fiber. So I would like to show you in the coming slide that how the refractive index difference is maintained and how DIR will occur in the next slide. Okay. So light can be taken anywhere using the optical fiber. It is used, these optical fibers are now used in data communication, for designing of medical instruments like fine endoscopes which can enter inside our body and see what is happening and click a picture of that. Micro-sized microscopes are being made using this optical fiber. So what is the composition of this optical fiber? So in the middle there is a core which is having a very high value of refractive index. Then that core is surrounded by a cladding. Obviously we want a TIR phenomena. So core is a denser medium. Cladding acts as a rarer medium. Cladding refractive index is always less than the core refractive index. Okay, which is made up of silica glass or plastic. So it can be a glass one, it can be a plastic one, any kind. Okay. Now these fibers are highly flexible in nature. We can bend it, mold it in any form to transmit the data from it. Okay, so it is highly flexible and durable in nature. So core is the one which is responsible for transmitting the signals and data, and cladding is actually forming an interface with core which is helping the light to be guided inside the core. So TIR phenomena is occurring at the core clad interface. Okay. Since the light is guided through the fiber, it is sometimes called an optical waveguide also, because we are guiding the light wave through the fiber. This is the structure. As I told you, in the middle it's a core which is having a denser medium, cladding is having a rarer medium, and then buffer and jacket, it is for protection from the wear and tear from the environmental conditions. Okay, here you can see the light is entering at an angle such that incident angle at core clad interface is greater than the critical angle, then only it is getting reflected back. Okay, this is how optical fiber works. Okay. Now there was one more term. Light gathering ability means how much light can be guided through this optical fiber depending on its core diameter. Okay, so core diameter will be deciding it, even the material. Okay, and other thing is acceptance angle. Acceptance angle is a light cone. Light cone or the maximum angle at which light can be guided through the optical fiber. Maximum angle of incidence at if it's actually giving you a threshold value. Like if your light is um, incident on this core cloud interface, at the core interface at an angle greater than acceptance angle, then it won't be guided. It has to be. It has to be within the range of acceptance angle. Then only it will be guided. Why so? Because those light waves which are entering outside the acceptance angle range, they will not exhibit the phenomena of total internal reflection. Okay. So outside also we have created a threshold, or you can say a parameter, that acceptance angle is there through which light cone must be incident, and then obviously those light waves which are coming through that acceptance cone, they will be guided because their incident angle at core cloud interface will always be greater than the critical angle. So that is the phenomena how it is working. Okay, is it clear to everyone? Is it clear, clear class?
Yes, ma'am.
Okay. Then comes the numerical aperture, how we will be calculating in our today's experiment. So here you can see there is a laser light source. Then optical fiber is connected here. Connector is there to connect, and then what we are going to do, we are going to vary this distance L, capital L, we will be varying today. Okay, like you must all have seen, like you can see this is a screen, output screen. Okay, this is the output screen on which you can see concentric rings or circles. So all of you must have tried during your childhood days, like holding a torch inside a dark room. What happens when you go towards the wall and when you go away from the wall, class?
Ma'am, towards the wall, diameter of that circle decreases, and away from the wall, diameter of that circle increases.
Yes,
Ma'am, but
yes.
brightness increases as we move closer.
No, diameter decreases as we
Ma'am,
move.
brightness,
Yes, brightness,
intensity, you see.
intensity. Perfect, perfect, perfect. And as we go far away, it becomes blurred, and it the light diverges out, right? So I would like to tell you this is not the pattern that we are going to get today, but yes, we will be getting a single circle at one time. So this diagram is showing you that different circles are formed at different times. Okay. Once you are closest to this the screen, you will get a smaller circle. As you keep on moving away from the screen, you will get a bigger circle. Getting my point? This diagram is showing you that particular part, and depending on the L value, your R value will change. Depending on the L value, your R value will change. So you will be calculating. So for every value of L, you will be getting a same value of numerical aperture. Getting my point? You will be taking different readings. Okay. So this is a acceptance angle, a theta value, and sine of theta is perpendicular upon hypotenuse. Hypotenuse is under root r square plus l square as per the Pythagoras theorem. R is the radius of this particular circle which is seen on the screen, depending on the distance L, distance between the source and screen. Okay. So sine of theta A is equal to r upon under root L, r square plus L square. This formula will be used to calculate the numerical aperture. And sine inverse of this particular value gives the acceptance angle. Is it clear to all?
Now, what will be presented on the screen? A circle, or a ring or a disc?
I will just show you through the virtual
Ma'am,
experiment. Okay, I will perform one reading for you all.
ma'am, the numerical aperture will remain constant.
Yes, yes, obviously.
Okay, ma'am.
Because it is telling about the optical fiber quality, what is the light gathering power. Okay, because as we are changing L, R is also changing now, so it will be compensated here. You will be taking a mean value like that. Okay, so this is the procedure. Let me show you how to perform this experiment straight away. Let's not read the procedure for this. Okay, but remember one thing, there are two distances, detector distance Z, detector distance X. Z is the distance between source and detector. Okay, and X is showing you detector distance, that is toward left to right of the fiber. Okay, so let me show you through that particular experiment. Again, you have to go to Amrita lab for that. So what you can do, the link is there on my slide. So by simply clicking on it, we can go to the optical fiber experiment. Yeah, can you see my screen, everyone?
Yes, ma'am.
Okay, so first of all, the instruction is place the apparatus in correct order on the breadboard to start the experiment. So I will place the apparatus in the perfect order. First, the emitter will come. This is a laser light source, okay, emitter. Then after emitter, we need a concentrator too. It is acting like a convex lens only, okay. Convex lens setup is there to converge the light waves, okay. Then we need to have a fiber stand such that we can connect the fiber. If I try to drag fiber, I'm not able to do that. First, I need to have a current output here and then detector. Now I will be dragging my optical fiber in the end. Is it clear to everyone?
You can
Emitter,
explain the positioning again.
this is emitter, emitter of laser light source. Second is your concentrator, which will be concentrating or converging the light. Then is your optical fiber, but you have to place optical fiber in the end once you have placed all the instruments. Then this is a stand, okay, fiber stand, where optical fiber will be clamped in. Then this is the detector, which is detecting the light rays. And in the end, we are converting the light signal into current form. We will be taking readings in current, okay, current units. So current output unit is there. Is it clear? Class, you know what will happen
Yes, ma'am.
if you don't place the instrument in correct place, they will go back to their original position. So not to worry, you can even try doing multiple things, but you won't be able to do that because if you are not placing it correct place, they will go back to their blocks, okay. And there are in total six things are there, so not to worry much about, okay. So once I click on start on the right hand side, everything has appeared here, right? Then I have to click on switch on button, so light is on now. So you can see the circle here. So I told you, you will be taking reading. This is a detection output unit, which is actually noting down the current value. Current. Okay. And current value is in microamperes. Class, listen to me very carefully. This is a current detector. Units are microampere. Clear? Okay. Class, be active. Why you guys so like lazy today? Be active. You're not responding back. Okay, then we have selected a fiber as glass fiber and select laser as red. Okay, so we are able to see this particular colored laser. So detector distance need to be fixed at some point. Like I have fixed it at any point, but you don't have to. You have to fix it. You don't have to change the value. So it is fixed to 4 millimeter. Now what you will be doing? This is a screw gauge, you can see. This is here only. So by clicking on this arrow, you can move the screw gauge. So what you have to do, you have to vary distance x. Distance between source and detector, that is capital L value. ये capital L value है, you will be varying this value and noting down the current in the output. Current देखो यहाँ change हो रहा है. This is again in microamperes. Getting my point? डिटेक्टर डिस्टेंस एक्स वेरी करोगे, रीडिंग यहाँ पे लोगे, डिस्टेंस एल का क्या वैल्यू है, एंड देन यू विल बी looking at the current output. Now let me show you the table, the observation table, then only you will be able to correlate it. So as you can see, serial number is there, so you can put 1 2 3 and so on. Screw gauge reading, which is giving you L value, capital L value. करंट इज इन माइक्रोएम्पियर्स, वो आप इजीली नोट कर पा रहे हो वहां से डिटेक्टर से. This is actually main scale reading column. This is a circular scale reading column. And circular scale reading will be multiplied by which quantity? बोलो बच्चों.
Least count.
Least count. Please, you can be on unmute, okay? So it is multiplied by the least count, okay? And then you will be adding both of them to get the complete value of distance between source and detector, that is the L value, okay? In millimeters. So you have to take these readings on this side, and then we have also this column they can also be consumed, and then you have to plot this graph, distance versus current graph. You will get this kind of plotting, and when you take 1 by e times the exponential decay of current, okay, 1 by e times of this maximum peak which is coming out to be here, this will give you the value of diameter d. ये आपको diameter d की value देगा. Okay, this is coming out to be d value, and once you do it d upon 2, do d upon 2, you will get the value of r here. This is how you are getting the value of radius, and this radius value will be used here in this particular formula to get the value of numerical aperture. Okay, is it clear, class?
Yes, ma'am.
Okay, just
मैम कितनी रीडिंग